Hello everyone and welcome back as we explore our second main application for this class. The second main application of this class is how Calculus 2 and both definite integrals and indefinite integrals are used in physics to help us to understand the behavior of a moving object. The study in physics of moving objects is what's called kinematics. And if you have taken any physics before, you may recall that you were given this big list of kinematics equations. Probably they just asked you to memorize it and use it, right? And what we're going to be doing today and tomorrow is we are going to be learning where those kinematics equations come from, and how the ideas of Calculus 2 were used to create and come up with some of those kinematics equations. So let's go ahead and get started. So the first thing that I would like to remind us of is that the quantities position, velocity, and acceleration are related by the derivative. If you have a function that tells you an object's position at time t, and if you take the derivative with respect to time, then the derivative tells you the rate of change of position, which is what we call the velocity of the moving object. Now, if you go one step further and you want to know how the object's velocity is changing over time, then you can take one more derivative with respect to time, and that gives you what we call acceleration. Acceleration is the rate of change of the object's velocity. So in Calculus 1, I could say, okay, here you go. Here is an object's position function. From that position function, tell me the object's velocity. And from that object's velocity, tell me the object's acceleration. You can move from position to those other two functions just by taking the derivative using Calculus 1 techniques. Well, we have learned that the derivative and the indefinite integral are basically opposites of one another. If the derivative goes forward, then the antiderivative goes backward through this list. And so the antiderivative can be used to take acceleration and reconstruct velocity. The antiderivative can be used to take velocity and reconstruct what the position function must have been. So now, using Calculus 2 techniques, I can say, here's the object's acceleration, find me the velocity of the object, and then find me the function that predicts its position at any given time. However, using this approach to reconstruct velocity from acceleration, using this approach to reconstruct position from velocity has one major issue associated with it. We know, for example, that position must be an antiderivative of velocity because velocity is a derivative of position. However, we have also observed that every function has several different antiderivatives. So the question is, position is an antiderivative of velocity, but which antiderivative is it? How do we figure out which antiderivative of velocity is our position function? Now, to show you how we address this issue in these calculations, I'm going to walk you through the following exercise. In order to address this issue, we need a little bit of additional information about our moving object. Namely, we need to know what our object is doing at one instant in time. Typically, we need to know what our object is doing at the initial time. And to show you what I mean, consider this exercise. We have a function a of t equals cosine of t plus 9 meters per second squared. And this function is what's telling you the acceleration of a certain object at any given time t. Now, someone says that at the very start of this problem, at the initial time when t is equal to 0, we have measured the object's velocity at that one initial time, and the initial velocity was 20 meters per second at that one initial time. We have also measured the object's position at that initial time. The object's position at time 0 was 3 meters. So from this information, let's go ahead and try to find a function v of t, which tells you the object's velocity at any time t. So what we're trying to do in this exercise is we're trying to take acceleration and we're trying to find velocity. So the first observation that I'm going to write down is that velocity is an antiderivative of a of t, of the acceleration function. The only thing is that we don't know which antiderivative it is. However, the indefinite integral is a description of all possible antiderivatives. So let's write down the format of all possible derivatives of the acceleration function. The integral of cosine of t plus 9 with respect to time. Now, if I write down this indefinite integral describing all possible antiderivatives of this acceleration function, then cosine of t becomes sine of t, 9 becomes 9 times t, and then because we're describing all possible antiderivatives, we know that some constant, any constant in theory, could be in the back. Now, since this is the description of all antiderivatives of the acceleration, and velocity is one of these antiderivatives, then the velocity must be equal to one of these functions for some specific value of c. We just need to figure out what specific constant c corresponds to the velocity function in this situation. Now, do you have any ideas of all the information in the question? Can you think of any piece of data in this problem that might help us to find the specific value of c that corresponds to this one particular antiderivative of this function? Well, we are told by the problem that the initial velocity should be 20 units, right? We are told by the problem that the object's initial velocity, the velocity at time 0, was measured to be 20 meters per second. So I'm going to basically plug that data into this expression here. I'm going to plug in t equals 0 for initial, and I'm going to plug in velocity 20 based on this data. And when I plug in t equals 0 and velocity 20, let's see what this equation tells me. On the left-hand side, the velocity is 20. On the right-hand side, the t values are 0. And by simplifying that expression, sine of 0 vanishes, 9 times 0 vanishes, and so I get 20 equals c. So, from plugging in this one piece of data about what the velocity was equal to at this initial time, then this equation was able to tell me exactly what a c value I had to have in order for this function to be the correct antiderivative of acceleration. And putting that c value back into position here at the end of the formula, now I have the knowledge that the velocity at any given time for this object is sine of t plus 9 times t plus 20. This function will tell you the velocity of your object in meters per second at any given time. Now, let's also take this one step further, and let's go ahead and try to find the position of this object at any given time. Let's try and find a function, I'll call it s of t, which predicts that position. Now, once again, scrolling back up, we remember that position is an antiderivative of velocity. So now that we found the velocity function, we just have to go through that whole process one more time to go from velocity back up to position. So taking note of that, position is an antiderivative of velocity. All the antiderivatives of velocity have the format given by the indefinite integral of the velocity function. So I copy paste that velocity function from part A of this problem. Now if I go to find this indefinite integral, then sine of t becomes minus cosine of t. 9t becomes 9 over 2t squared by power rule, and then 20 becomes 20t by power rule. And then any constant, in theory, can be here in the back. And our position function must be of this format. We just don't know right now what specific value of c corresponds to the specific position function for my object in this scenario. So what am I going to do to help me to find the specific c value for this function in this scenario? I'm going to go back to the question and I'm going to go searching for any information that might tell me a little bit more about what's going on with the object's position. And I can see that information right here. The object's initial position, the position at time 0, is supposed to be 3 meters. So I'm going to put that information in here. Initial position should be 3. So I'm going to plug in t equals 0 for initial, and I'm going to plug in a position of 3 to this formula to see what it tells me about what the constant needs to be. So the position on the left side needs to be 3. The time is 0 because we're told that this is the initial position. Now, if I simplify this, negative cosine of 0 becomes negative 1. This term here vanishes, 9 over 2, 0 squared. This term vanishes of 20 times 0. So I'm left on the right side with negative 1 plus c. And that forces the value of c to be equal to 4. So using that piece of data allowed me to figure out what specific c value would correspond to my position function. And if I put that c value into its position at the end of this expression, in that situation, we would get a position function, which is equal to, copy paste the negative cosine, copy paste the 9 over 2t squared, copy paste the 20t, and then we know the c for this particular function, for this particular antiderivative, should be 4. So this is how we use acceleration to find velocity and to find position. If you know the acceleration function, and if you also know the initial position, and you also know the initial velocity, then with those two sort of extra pieces of information, you can find the velocity at any time for your object, and you can find the position at any time for your object. Let's explore this idea in one very special situation where the object has a very special acceleration function. So an object is said to be in free fall if the only force which is causing that object to move is the force of gravity. This is the kind of situation that you can encounter if you have an object which is falling in a vacuum. If you have an object that's falling in a vacuum, then gravity is pulling that object downward, and you don't really have any other forces like air resistance or fluid resistance, which are also affecting that object's movement. So an object falling in a vacuum is said to be in free fall. Now, when an object is in free fall, falling, for example, in a vacuum, it behaves in a really, really interesting way. The acceleration of the object when it is in free fall is actually constant. And the constant acceleration for an object in free fall is nicknamed appropriately the acceleration due to gravity, the acceleration that is caused by gravity alone. And this constant acceleration has actually been measured, and the size of this constant on Earth near sea level is roughly speaking about 9.81 meters per second squared. This acceleration gets smaller as you move away from the Earth's center, as you climb to the peak of a mountain. But the acceleration due to gravity doesn't actually change very much as you move up and down that mountainside. This estimate of 9.1 or 9.8 can be used in many scenarios on Earth. Now, if you have an object falling in a vacuum, let's try mathematically to find the function that predicts the object's position at any given time. This extremely famous physics equation for the motion of an object falling in a vacuum. So, if you have an object falling in a vacuum, we've just said that the object's acceleration is constant. The acceleration function, in other words, is given by this formula right here. Acceleration is equal to negative this constant g, where g, its specific value depends on what planet you're on and what elevation you're at. Thought exercise. Why does this g have a minus sign attached to it? That's because if an object is falling, then of course the object is accelerating downward. It's going faster and faster in the downward direction. And to capture that, the acceleration is given this negative sign, negative acceleration to indicate that it's going faster in the downward direction. From this constant acceleration function, let's go ahead and find the object's velocity function. Now we remember that velocity is just an antiderivative of acceleration with respect to time. And so I just need to figure out precisely which antiderivative it is equal to. Using the indefinite integral, I'm going to start by writing down the format of all possible antiderivatives. If I integrate this number minus g, then the integral of a number is just number times variable. So negative g times t in our case. And then we have the unknown constant here plus c in the back. Now, in the previous exercise, we saw that if we wanted to know the specific value of c, then we need some additional information about the velocity at one specific time. For example, the velocity at the initial time. Now, in this problem, we do not know the initial velocity exactly, but we are given symbolic notation. We're going to call the initial velocity v with a subscript of 0, just generically. So let's go ahead and plug in a time of 0 for the word initial, and let's go ahead and plug in a velocity of what we're calling v naught for short. And then if we do that, we get v naught is equal to negative g times 0 plus c implies that the constant in this case of free fall is exactly equal to the initial velocity. And so putting that back in, we get our velocity function, negative g times the amount of time that has passed plus your initial velocity. If you know the initial velocity and you have your acceleration due to gravity, then you can use this formula to predict the object's velocity at any future time, t. Now, if you go online and you look at the kinematics equations from physics, you can see this formula show up once again exactly, although the notation might be slightly different. For example, here, if you're looking at the height of an object that's a projectile, then the acceleration can be thought of as constant, this negative 9.8, approximately speaking. And the velocity in the vertical direction at any given time can be found by taking negative g times t and then combining that with the initial velocity. So here is that kinematic equation for a projectile object. And you see that over here as well in this example. It's just that their notation is a little bit different. Here they're using a instead of g for the acceleration due to gravity. And I think they're probably assuming that a is a negative number, that this is negative 9.81. So now that we found the very famous kinematic equation for the velocity of the object, let's go ahead and find the position of the object. Let's go ahead and find that function. So once again, the position of the object is just going to be one specific antiderivative of the velocity function. So using the indefinite integral, I'm going to write down all possible antiderivatives, and then I'm going to figure out specifically which c corresponds to the scenario in my problem. So each of these terms can be integrated using power rule and constant multiple rule. This term in the front, negative g times t, just copy pasting that negative g, that constant multiple. I apply power rule to t and I get t to the power 2 all over 2. V sub 0 is also a constant, the initial velocity. So the integral of that constant will again be constant times variable, v naught times t. And then we have this plus c in the back, representing this unknown added constant. So let's try and figure out what that constant would be in the notation of this scenario. Now we are told that the object's initial position is something that we're going to generically just call s with a subscript of 0. So if I plug in t equals 0 for initial, and if I plug in a corresponding position of s naught, then I get negative g over 2, 0 squared v naught, 0, and then plus c. And after simplification, we can see that this means that the c in this step of the problem has to be exactly equal to the initial position of the object. And so from that, we get this problem representing the object's position at any given time. And so from that, we get this equation representing the object's position at any given time. Negative g over 2 t squared, then v naught t, and then plus s naught. So negative acceleration due to gravity, cut that in half, multiply that by t squared. Then the initial velocity multiplied by t, and then the initial position here in the back added. This formula can be used to predict the object's vertical position at any later time. So you get a lot of fun exercises and experiments and examples of motion that follows this formula. This, for example, can be used to, roughly speaking, predict the position of an object which is launched, for example, by a catapult. It's very common in campuses to have an experiment where you put a watermelon into a catapult and then launch it to see if you can predict where the watermelon will end up. I have also recently been playing Breath of the Wild, and those of you who have played that game may know that you can launch objects in that game. And when you launch objects in that game, you can use this kind of formula to predict where the object will land. Okay, that concludes today's video. Today we talked about indefinite integrals as they applied to motion and how the indefinite integral can be used to calculate velocity from acceleration and position from velocity. Tomorrow, we are going to be talking about how to apply the definite integral to motion problems like this one, and how the definite integral can be used to calculate, for example, the total distance traveled by an object.